Okay, welcome to Lecture 9 for Unit 1, First Order Differential Equations. And today we're going to be looking at modeling with first order ODEs. So where are these first order ODEs that we've been studying, where are they useful? Okay, and the two examples we'll be looking at are compartmental systems. So I'll explain to you what that is shortly. And Newton's law of cooling and warming. Okay, so a compartmental systems model is one of the simplest but also one of the most useful models in applied mathematics. Okay, and so the premise is actually really simple. The idea is we have some compartment, which I'm representing by the box in the middle of the screen here, and inside this compartment there is something inside this compartment. So for example, it could be the amount of pollution within a river, or it could be something in the context of disease dynamics. It could be the number of people that have a certain disease like chickenpox. But the idea is there is some input rate, that is there is some amount of the substance entering into this compartment, and there is some amount of the substance exiting the compartment. So we're going to let x, which is a function of time, so I'm going to write it x of t like so. I'm going to let this represent the amount of a substance in the compartment, okay, at some time t. So perhaps if we think of this as pollution in a river, there is some input going into the river, let's say washing over the land, into the river. So there's some input rate of pollutant into the river, and there is some output rate of pollutant, let's say, as either the pollution gets processed by plankton and algae and things like that, or it just gets swept out to sea or something. So there's some flow into the river of pollutant, there's some flow out of the river, and x of t represents the amount of that pollutant in this particular river. Okay, so at any time we have input and output rates which tell us the rate at which the substance enters and exits the compartment. And we can write this as an ordinary differential equation. Okay, so this is quite simple. The rate of change, dx by dt, so as time changes, as time evolves, as time moves forward, how is the amount of the substance in the compartment changing? Well, this dx by dt is equal to the rate of change of the substance in the compartment. Which of course we're assuming the only way that the amount of substance can change within that compartment is it can either increase because something's entering the compartment, or it can decrease because something is leaving the compartment. So we can simplify this ODE as just in terms of words. We can say dx by dt, the rate of change of the substance in the compartment, or let's say the pollutant in the river, is equal to the input rate minus the output rate. Okay, so if the input rate was exactly matched to the output rate, for example, dx by dt would be 0, and the amount of, well, let's say the substance or the amount of pollution in this compartment would be constant. But if say the input rate of a substance into the compartment was less than the output rate, then dx by dt would be negative, and therefore the amount of substance in the compartment would be decreasing. Okay, so an extremely simple model, but very powerful and very useful in applied mathematics, especially when we have multiple compartments. We can create quite complex models with fairly simple differential equations. Okay, but for us, we're just going to focus on one compartment. And so let's look at an example of that. So let's imagine we're building a saltwater aquarium for a local dive shop. And this dive shop has purchased a 1,000 litre tank, so it can hold quite a lot of water. Initially, this tank is filled up with pure water, but they want it to be a saltwater tank. So they pump a salt brine solution into the tank at a rate of 6 litres per minute. Okay. the tank is kept well stirred, so we can assume that if we test the saltiness of the tank at any point in the tank that it's equal. So that's what we mean by well stirred. The salt gets well distributed throughout the tank. And we say that the mixture of this water and salt brine solution flows out of the tank at 6 liters per minute, so the exact same inflow rate. And the reason that is to keep the tank at a constant volume of 1,000 liters. So we've got this tank which is initially filled with pure water. We pump in a salty, very salty, briny solution into the tank at a rate of 6 liters per minute, and we pump out this mixture of this nice pure water and the salty solution at the same rate to keep the volume of the tank constant. Okay, and so we're also told that the salt brine solution that we're pumping into the tank has a concentration of 100 grams of salt for every liter of water. Okay, so the question that we need to answer is, when will the concentration of salt in the tank reach 50 grams per liter? Okay, so let's think about this for a second before we write down any differential equations. We have this tank which initially has a salt concentration of 0 grams per liter because it's pure water, right? So initially we have no salt in that tank at all. And we start pumping the salt brine mixture into the tank at a rate of 6 liters per minute, and that mixture that we're pumping into the tank has a concentration of 100 grams of salt for every liter. Okay, so this brine mixture enters the tank, mixes well with the pure water, becomes a little bit salty. The pure water becomes a little bit salty, and then that mixture gets pumped out at 6 liters per minute. Okay, so this is a classical compartmental system model. We have a tank, we're pumping something in, and we're taking something out. So we're going to recall that we can represent our compartmental systems model using the ODE. dx by dt equals the input rate minus the output rate. And so we need to write algebraic relations for the input and output rates using the information given in the problem. Okay. So the key information there I've highlighted in red. And so let's use that information to complete this model. So X, I should say here, X is the mass of salt in the tank at time t. So initially X, that mass of salt, is going to be 0 grams. Okay, so I've just extracted this most key information that I've highlighted here in red. I've extracted that and put it on the next page just to make it a bit easier for us. So again, as I said, X of t is the mass of salt in the tank at time t. The input rate of salt, okay, well, we are pumping in 6 liters of fluid per minute. It was per minute, wasn't it? Yes, good. And we know that fluid we're pumping in, that salt brine solution, has a concentration of 100 grams per liter. Okay, so 6 liters per minute multiplied by 100 grams per liter. Well, if you look at the units here, we have liters per minute multiplied by grams per liter. So the liters are going to cancel out, and we're going to get grams per minute if we multiply these things together. So if you multiply 6 liters per minute multiplied by 100 grams per liter, the amount of salt that is actually entering the tank is 600 grams per minute. Okay. So now we have a rate at which mass is being pumped into the tank, the input rate. Okay. The output rate is a little bit harder. Okay, there's a little bit more work involved with the output rate because, well, we don't. In fact, the concentration of the salt in the tank is changing over time, right? It's initially 0 salt in there, so x of t equals 0, so there's 0 grams per litre in the tank initially. But as we pump more and more salt into the tank, the concentration of salt in the tank at time t is the current mass that's in the tank divided by the tank volume. So the current mass, if you recall, at time t was just x of t, and then the volume of the tank was 1,000 litres. So the concentration of salt in the tank at time t is x over 1,000 grams per litre. And of course we're pumping this saltwater mixture out of the tank at the same rate as we're inputting it, so 6 litres per minute. So the output rate of salt from this tank is 6 litres per minute multiplied by x over 1,000 grams per litre. Again, we have a litre on the numerator over here and a litre on the denominator over here. So if you multiply those, they cancel to 1. So we end up with 6x over 1,000 grams per litre. Or if I simplify that, 3 over 500 times x grams per minute, not grams per litre. Okay, so key points there. Input rate is 600 grams per minute. Output rate is 3 over 500 times x grams per minute, where x is the mass of salt in the tank at time t. So therefore we can write our differential equation, or in fact our initial value problem, like so. So the rate of change of the salt in the tank is equal to the input rate, 600 grams per minute, minus the output rate, 3x over 500 grams per minute, and our initial condition is there is no salt in the tank. So at time 0, the amount of salt in the tank is 0 grams. Because initially we have pure water. Okay, well let's look at this. Let's study this differential equation and this initial value problem. So let's notice then that this ODE is separable, right? I can multiply both sides by dt. I can divide both sides by the right hand side of the ODE here, and we would have, well, I would have a separable ODE, okay? Like so. So we can integrate both sides of this equation, the left side by dx, the right hand side by dt, and well, it's not too hard an integral, and hopefully you can convince yourself that the solution to that integral is going to contain a logarithm, because we've got a number over x here. So the solution to that ODE, perhaps you'd like to check, is negative 500 over 3 times the log of 600 minus 3 over 500x. Okay, and that is equal to, so on the right hand side we integrated 1 with respect to t, so that equals t plus some integration constant. Okay, but we really want to simplify this equation, because what we really would like is an expression for x. If we can, we'd like that to be explicit. So what we're going to do is we're going to multiply this equation, or this our solution, by negative 3 over 500 to eliminate this leading term here. And then to get rid of the logarithm, we're going to take an exponential. So if I do those two things, on the left hand side I get left with just 600 minus 3 over 500x. And on the right hand side I have, I've taken the exponential. So I have negative 3 over 500t, the exponential of negative 3 over 500t, times some constant a, which is the plus or minus the exponential of the integration constant. Okay, and of course we can rearrange this to get x on its own by subtracting 600 and then multiplying by negative 500 over 3. Okay, and we can also find the initial condition, or the constant a, by using the initial condition. Okay, so the initial condition being at time 0, the amount of mass, or the amount of salt mass in the tank is 0 grams. And if we enter that into the differential equation, what you should find is that a equals 600. Okay, and actually it's not too hard to see from this line why that's true, because if I substitute in t equals 0 here, we get the exponential of 0, which is 1. So our right hand side is a, and on the left hand side, when t equals 0, x equals 0, so this term is 0, and we just get left with 600. So a equals 600. Therefore, we can represent our solution, the amount of salt in the tank over time, as 100,000 times 1 minus the exponential of minus 3 over 500t. Okay, so this describes the mass of salt in grams in the tank at any time. Okay, that's great. We've solved this differential equation, and in fact, we've solved this initial value problem. We've done the mathematics part of it, but this is not the question we were initially asked, right? Initially, we were asked, when will the concentration of salt in the tank reach 50 grams per litre? So this is the question we actually wanted to solve. Well, we can actually answer this question using our solution now, of course. So what we want to know, what we wish to know, is that we want to know at what time will the concentration be 50 grams per litre. That is, when will x equal, at what time will we have 50 grams per litre in our tank? Okay, it's not quite as simple as setting x equal 50, because recall x is the mass in the tank, so that's in grams, but we're actually looking at a concentration. We're looking at grams per litre, so we have to take into account that our tank has a volume. Okay, so our tank is 1,000 litres in volume. Okay, so how much mass do we need in our tank for our concentration to be 50 grams per litre if we have a 1,000 litre tank? Well, quite simply, x is going to have to be 50 times 1,000 then. 50,000 grams. Okay, turn that to kilograms if you like, 50 kilos of salt. Okay, well, let's just double check why that is, because if I take 50,000 grams of salt and I divide it by 1,000 litres, then I just end up with 50 grams per litre if you do that mathematics. Okay, so the concentration, when will the question is, when will the concentration of salt in the tank reach 50 grams per litre? It's when x equals 50,000 grams. So if x equals 50,000 grams, our left-hand side of our solution to our initial value problem is 50,000. Now we need to rearrange this equation to make t the subject of the formula. So what I'm going to do is I'm going to multiply through into this bracket, this 100,000. So I get 100,000 minus 100,000 times this exponential, and subtract this 100,000 and divide through by negative 100,000. So I get negative 50,000 plus 100,000 over 100,000. Okay, which of course I can simplify, because this is just simply going to be 1/2. I probably could have simplified that earlier. And then I can take the log of both sides to make the right hand side negative 3 over 500 times t. Okay, so that we end up with the log of 1/2, so this is 1/2. The log of 1/2 equals negative 3 over 500 times t. I can easily then multiply both sides by negative 500 over 3 to get t by itself, right? And if I do that, I find out that the time it takes for the concentration in the tank to reach 50 grams per litre is about 115 minutes, just over 115 minutes. Okay, so I can go to my local dive shop and say, well, I need a couple of hours of your time to get this tank up to the right saltiness so that you can have all your marine life happy in that tank. Okay, so this was a very, I guess, fairly simple application of first order ODEs, and in fact compartmental systems in particular. These compartmental models are extremely common and extremely useful in applied mathematics. So if you continue your mathematics career, I'm sure you will see them again. Okay, so slightly changing tack now. We want to look at a physics problem which obviously Sir Isaac Newton had worked on. So something called Newton's law of cooling and heating. And so what this law says the change of temperature of an object over time can be described using a first order separable ODE. Okay, and this ODE is the rate of change of temperature T over time. Okay, so as time evolves, temperature changes, is equal to K, where K is some real number, some constant, times the temperature minus this thing TA. So let's define these things. T is the object temperature at time T. T sub A is what we call the ambient or the room temperature. Okay, and K is just some constant. So we have this lovely differential equation which describes how objects, let's say hot objects placed in cool rooms, how the object cools down over time, or the opposite, right? A cold object, so if T is small and the ambient temperature is large, how that object heats up over time. So, well, let's just say we've got our cake. We've mixed up a cake and we need to cook it. So our cake is initially at room temperature, let's say 20 degrees Celsius. We chuck it in an oven which is at 180 degrees Celsius. So our ambient or oven temperature would be 180. So this differential equation is going to describe how the temperature of that cake changes. Okay. So let's look at an example of this. So, well, I didn't use a cake. I dropped a can of Coke, apparently. So my example is I dropped a can of Coke, which is initially at 20 degrees, into boiling water. This must have been some kind of science experiment. So after only 1 second, somehow I knew that the temperature of the can had increased by 2 degrees Celsius. So I'm kind of assuming here that the can heats up as one mass, one body, which is obviously a simplification, but let's go with it for now. Okay, so my question is, how long does it take for the can to reach 90 degrees Celsius? How long does it take to reach 98 degrees Celsius? So actually there's two questions there. Okay, so what do I know here? Well, I know that Newton's law of cooling says that the heating of this can should follow this differential equation, this first order linear and in fact separable ordinary differential equation. Okay, if we're assuming we're at sea level, then water boils at 100 degrees Celsius. Hence our ambient temperature is 100 degrees Celsius. So TA in this differential equation is 100. So I can add that into the differential equation. And again, this is a very simple differential equation to solve. It's separable. So again, I think this is easy enough that you should be confident to be able to solve this. So what I'd like you to do is to go away and make sure that if you solve this differential equation in its current form, you find that the temperature at time t is equal to 100 plus c naught, the integration constant, times the exponential of k times time. So k is again that constant in our differential equation. It's just a real number that we don't know yet. Okay, well I say it's a two-parameter family of solutions, the ODE, because we have two parameters, C naught and K. If you go away and you try to solve this ODE and you don't get the same thing as I do, please get in touch and I'll help you to work through the steps. And we can find out where the issue is. Okay, so what we need to do now is we need to find the value of these parameters, C naught and K. Okay, well that's okay because we know two things, right? we know at time t equals 0, we know that the can was at 20 degrees Celsius, because the can was initially at 20 degrees Celsius. We also know that at time t equals 1 second, the can was at 22 degrees Celsius, because they said after 1 second, the temperature of the can increased by 2 degrees Celsius. Okay, so we can represent this information that we know as some initial conditions, or some an initial condition, T0 equals 20. Okay, so when time equals 0, t equals 0, temperature equals 20, we can put that in the differential equation. So 20 equals 100 plus C0 e to the k times 0. Okay, well, e to the 0 is just 1. So therefore this right hand side just becomes, well, this equation, let's say, becomes 20 equals 100 plus C0. And therefore we can solve for the value of C0 and find that C0 is equal to minus 80. Okay, but we also know a little bit more information, right? We can solve for C0, but we also know that when t equals 1, when time equals 1, the temperature, capital T, is equal to 22 degrees Celsius. So now we can substitute that into our differential equation as well. So 100, well, now I've said that C0 is minus 80, so 100 minus 80 times e to the k times 1, because time t, little t, was equal to 1. And now I can rearrange this equation to find the value of k, right? I can subtract 100 from both sides, so 22 minus 100 divided by negative 80, whatever number that turns out to be. Then I can take the log of both sides of the equation and I'll get k. And if you do that, you should find that k is equal to some relatively small value, negative 0.0253. Okay, so now I've solved this initial value problem, right? I found the value of C0, which was negative 80. I found the value of k, which is negative 0.0253, which is great. So I've got this lovely solution that changes over time. But again, this solution doesn't answer the question, right? Because the question was actually, how long does it take for the can to reach 90 degrees Celsius? And how long does it take for the can to reach 98 degrees Celsius? Okay, so if this is our solution to our differential equation, we want to know when temperature, capital T, equals 90, what is time, little t? Okay, so substituting in the left-hand side, capital T, temperature equals 90. Again, we're just going to rearrange this equation for little t. So 90 minus 100 divided by negative 80, taking the log of that answer, and then divided by the log of that answer by negative 0.0253. That will give us the temperature. That will give us the time at which the temperature is 90 degrees. And if you do that, it turns out that is about 82.1 seconds. So this Coke is really heating up fast for some reason. Okay, well, the second part of our question was how long does it take to reach 98 degrees Celsius? Of course, we do effectively the same thing. When temperature equals 98 degrees Celsius, we substitute in 98 degrees on the left-hand side, and in fact we should find that it's about 145 seconds. So this is probably the fastest heating can of Coke in history, but okay, hopefully you get the idea that first order linear and nonlinear, in fact, differential equations are extremely useful in applied mathematics. And now, because we've finished Unit 1, you know how to solve them all. Okay, thank you very much.